Anyway, welcome to demos. We're recorded here, so I'm not going to get down too deep a rabbit hole of complaining about our perfect infrastructure. Our infrastructure is amazing and everybody loves it. It actually is really good. It's one of the reasons I stay on the team. Anyway, digression. Welcome to the demos meeting. We're so excited to have everybody here, both in person and whoever is reading later. Do we have a list of demos today? Did anybody sign up for a demo? So first up, we've got Alan. Take it away.
Oh, okay. Here we go. So the intro to this is the indexing service is brand new and not trivial. It's a little bit complicated. I haven't finished these diagrams, but I've done enough that I think it's worth maybe talking you through the first two types of diagrams that I've done, because it should give you an overview of the indexing service and how it works. Let me share my screen. Okay. Shout if you do not see that. Can I have control? Yes, okay, here we go. Cool. First of all, let's talk about some names for things that you should probably understand if you don't already. When we refer to a blob, we talk about like that. That's just a kind of opaque set of bytes that have been kind of asked to have been stored by our service. Doesn't matter what's in those bytes. We just view them as a chunk of bytes that are there. When we talk about a shard, that's actually a DAG, a directed acyclic graph that has that may have been split into multiple parts. Could be one shard, but it would have been done into multiple. It would have been split into multiple shards if the DAG got really big, for instance. Like a shard is just a blob. When your DAGs are sharded, we usually serialize them into something called a CAR, which is a content addressed archive, kind of like a tar file, but a CAR. Anyway, a slice is just a subset of bytes in a blob. It's like a slice of bytes in Go, or if you're in JS and you've got a uint8 array and you use the .slice method on that, you get back another chunk of bytes. So when we talk about slices, they're like a subset of bytes in a larger chunk, and they typically are the bytes plus like an offset and a length. And when we talk about a slice in the context of a shard, we're typically picking out a block or a node in the graph that is the DAG. So that's a slice. An index for us is this data structure. We actually have a spec for it written down in our specs repo. It's a data structure that like describes where the blocks of the DAG can be found within a shard of data. So it's typically a sharded DAG index is what we call it, because it's a special kind of index that tells you about the shards of a DAG and slices in each shard. And when we talk about slices, we're talking about obviously the bytes, the hashes, and the offsets and lengths. And the shards are the hashes of the shards that are there. And the index also includes the content SID or the root SID of the DAG, which is different to like the SID of like a blob as a whole or a shard as a whole. So super confusing, I know, but these are the terms that we are playing with here. So in the indexing service, we come across these, which is why I've written down just in case, just so people could understand. I've kind of left out invocations that are not really directly to the indexing node, which is over here. So for instance, like users will use the client and they'll make kind of invocations to our upload service, or W3up is what we call it. And the upload service talks to storage nodes, etc. But that's kind of by the by. The interesting ones that we're talking about here are the fact that these ones. So these are UCAN invocations, the arguments or the data that's actually included in them. So let's talk about the first one, which is when a storage node receives a blob, it will actually make an invocation to the indexer service to say, can you please cache this claim that I have? That's why it invokes this capability called claim cache, and it passes the SID of the claim in the invocation, and also some information about the address where that the claim and the blob that it's referring to can be fetched, and that just allows the indexer node to cache that information and serve it back to anyone who asks as soon as it gets asked. It caches this location claim because it needs to. It also puts this location claim in a IPNI chain, which we'll talk about in a little bit, but it needs to cache it in the indexer node for immediate retrieval because the IPNI chain it isn't instantly available in IPNI. It has to, you have to kind of wait for IPNI to sync your local chain to its remote state. So that can take an undefined amount of time. So by caching a claim in the indexer node, it can be immediately retrieved, which is kind of what we want and need. So this claim is actually a location commitment, and that is, so it's a SID here, it's linked, but it's actually attached to the invocation. So it is in that invocation. And this is kind of what it looks like. So the location commitment or location claim is an assert location ability, and it just says that the content. So when we talk about storage nodes in general, they're usually storing. They don't care what's in the content, but they just store blobs basically. The content. So this is the hash of a blob that got stored. It has the location, the URL to itself. And it also has information about the space that the blob is being stored in. And the space information is just there so that when it comes to serve that blob, the egress information can be attributed to this particular space. So that's the kind of the only invocation that a storage node makes to the indexer node right now. The other invocations that get made to an indexer node are from the upload service or W3up, and they happen in response to two things. So the assert index claim gets invoked on the indexer when an index add claim is index add invocation is sent by the user. So the user basically says, "I've got an index. Can you deal with that? Make the information in that index available so people can actually retrieve my stuff." The upload service can then verify that that information is correct, and it will then make a third index invocation to the indexer to say, "Okay, I've verified that that's all correct. The content is this kind of Baffy root SID, the SID of the DAG as a whole, and the index is this is the SID of the index that basically describes where you can find all of the slices and for that whole DAG." The other one is similarly, when we receive a Filecoin submit invocation from the client, it basically tells the service, "I'd like you to put this content, which is just a blob." It also tells us like the piece SID, which we need to kind of verify that those two SIDs actually match up or are equal, or equivalent in some way. And so once it's done that, it can make an assert equals claim to say this particular piece of content, this car file, this blob, this shard, you can also refer to this by this piece SID. And so it makes this invocation to the indexing node. The indexing node, when it receives these two invocations, actually it will cache that information, just like it will with this claim cache thing. But it also has its own IPNI chain that allows this information to become available after it leaves the cache, basically. So so I've referred to two kind of IPNI chains that exist now. let's look at how they work. For a storage node, let's zoom in. The kind of overview on IPNI chains, they're basically a list of adverts, and each advert points to the previous advert. And we say that this advert at the top is the head of the chain. And basically, when you create a new advert, you tell IPNI that a new advert is available, and IPNI comes and slurps up that information. The cool thing about adverts is that you can put some kind of information in here, but they have this thing called entries. And these are the list of SIDs that, that when you query IPNI, it will return the information in the advert. So you can basically have a many-to-one relationship between a piece of metadata and a bunch of SIDs. And those bunch of SIDs are typically, or I guess they are intended to be like the SIDs of a DAG. So your root SID and anything else that it links to all the way down to the leaves, so that you can then query for any SID in a particular DAG and still get the information about like who has it and whatever other metadata information you have. And effectively that allows random access. So you can, if you've got like a big file and you've got a SID of something in the middle, then you can go and get information about who has that and then get that SID from them. So the IPNI chain looks like this. For storage nodes, they only have one type of advertisement that they make, and that's for location claims, basically. Each advert has a context ID, which basically allows you to reference or like remove or change adverts, essentially. And for a storage node, this is a combination of the space did of the thing that was stored and the multi-hash of the blob that was being stored. The metadata in a storage node advert chain is basically a SID of the location commitment and expiry, and the entries are literally just the SID of the shard that has been stored. So every advert has one entry, which is the SID of the shard that was stored, or blob that was stored, essentially. So when you query IPNI for a SID of a blob, you'll get back information about the location commitment. And when you combine that with the advert information here, like the adverts, you see there's actually a special kind of HTTP path here. You should be able to fetch that location commitment by substituting. This actually looks like, this is percent encoded, but it looks like that when you substitute it. When you substitute the claim SID that's in the metadata here, you should be able to fetch that particular claim. And the same thing with blobs. So let's just open that back. Yeah, so, and that's how you actually can get hold of the location commitment. And then you can, because it's, if you remember from up here, location commitments look like this, you can then actually just get hold of the blob pretty easily for any given SID. So that's the storage node, really easy. It has its own chain because the storage node might actually need to change its address at some point. So this is, or we might need to move all of this data onto another node. And so what we're juggling here is kind of mutable data versus immutable data. And the indexer node IPNI chain basically deals with immutable data. So its adverts are either an index claim or an equals claim. So the index claim is created in response to an invocation to assert index. Looks similar. Context ID is just the index SID. The metadata is basically the SID of the index again. This is where it gets interesting. The entries here in a index claim, all of these are the multi-hashes of slices in that index. So for any block or any slice or any node of a DAG that you want to get hold of. If you query IPNI, then what you'll get back is a SID of an index. And once you have a SID of an index, then you can go and query an IPNI again and get a location claim to find out where the index is. And once you get the index, you know which shards your DAG can be found in, and you know like about all the blocks in the DAG and their offsets and lengths as well. So you can, at that point, you have all the information you need to retrieve a DAG in full. And either, if you're a gateway, you might want to combine, like recombine that into a file and send it back, or whatever you want to do with it, essentially. So that's index claim for an indexer node. The other type of advert that indexer nodes will have are equals claims, and they are, like I said, from a filecoin submit, and then once the upload service has verified, it will do a kind of assert equals claim. This is just saying that a given SID is equivalent to a piece SID. The context ID is the SID that the thing is equal to. The metadata is, again, we've got a SID of a claim, so we can actually go and verify that this equals SID is what was claimed. But yeah, all of this particular advert gives you all the information you need. So you can actually query IPNI and say, okay, I've got the multi-hash of a particular blob, and you'll get back a response which says this particular multi-hash, this is the PCID for it, which is pretty cool. And that's kind of it for the chains, and that's how to fit together. I didn't get around to doing the caches, but caches are going to be what I'm going to document next. But hopefully that makes it a little bit clearer as to what is being stored. And I've got lots of notes here on why things are the way they are as well. And I will commit this into our system architecture repo when I get a second. And that was my illustrated guide to the indexing service. Hopefully that was helpful.
Sure was. Thank you, Alan. That was great.
Questions?
And just a reminder for me and everybody else, this is recorded. So if you want to go back and watch the whole thing, then you can. And yeah, any questions about that? Cool. I think next up we've got Felipe. And that's it. Felipe is going to demo the gateway content serve authorization flow, part 1, the delegation store.
Yep.
I love a good part 1. And
let's go.
Part 2 coming in 2 weeks.
Hopefully. Actually, in the next 2 days, perhaps. It's the easiest part.
Amazing.
Yeah, so the part 1 is actually the part where we're gonna store the delegation. So just to give some context, the idea here is to create authorization for a gateway to serve content from the spaces. So when the user creates a new space using the new W3Up client, it will automatically grant the permission to the gateway to serve the content of the space. In the client will have the option to opt out and do not authorize the gateway. So the flow for that is basically this chart over here, where the client will be using the W3Up client and will create the space that will trigger a UCAN invocation in the freeway worker. It's a new endpoint in the worker, and that will process the invocation, and it will check if the invocation contains the valid delegation. And the valid delegation in this case is the space content served delegation. And this delegation grants not only the ability to serve the content, but also to record the egress. And if that is valid, we're going to store this in a delegation store in the Cloudflare KV. So that's part 1. Part 2 is basically sending a request to the worker and making sure it will fetch the delegation from the store and serve the content. But that's not done yet. So to give you a quick overview of this flow here, I have my own KV instantiated in Cloudflare. If I refresh this, you will see I don't have any key values stored in this store. So it's all like it's empty, and I have a test unit integration test pointing to my remote worker and deployed to Cloudflare. And this will trigger, like this basically creates a new space and grants the gateway the permission to serve the content from that space. So if I hit play here, it will trigger the call and will save this space in the KV with the delegation. So let's go. The results should be a delegation, the delegation that was stored. And if I go back to the KV, I should see the new delegation here. Let's see. There you go. It uses the space did key as the key of the map. And this is easy for us to fetch these delegations. The delegations are stored in a byte array. So we can fetch this in the gateway and verify if the delegation is present and then serve the content. And yeah, that's pretty much it.
Cool. Great. Any questions on that? All right. Let's see.